So, good afternoon. I'm going to talk in English, and you might have already understood it from the title of my master thesis, that is mostly about remote sensing, measuring deformations, and so on. But as a geologist, I'm also going to dive into topics related to geomechanics, underground excavations for industries like mining and tunneling, the industries I'm working in right now. Yeah, so the motivation here, however, was slightly different. It was about such a problem as nuclear waste management. And we know that for the most toxic, the most radioactive waste, deep geological disposal is sometimes considered. And in these times, such objects are built in three types of rocks, which are shales, rock salts, and the granites, which I'm going to talk about. And of course, to design to build such objects, we need some deeper understanding of the long-term rock behavior, of the geomechanical properties, and that was the motivation for our project. The project has a long name, we can just call it Pre-Code project for now. It is funded by the German Society for Nuclear Waste Management, and it has several participants here in Europe and also in the Northern America. The project's workflow includes numerical modeling, laboratory and field testings in geomechanics, but also LiDAR scanning. And this is what I was doing, measuring deformations, measuring rocks, long-term behavior. So I'm going to give a short site introduction, then I'm going to talk about the methodology of both field investigations and data processing, and show the results and discuss them just a bit. It all took place in the southern Switzerland, in the canton of Tessin, Ticino. This is where the Bedrette tunnel was built as a technical one in 1970s, 1980s during the construction of the Furka-based tunnel, and it wasn't used since then until in 2018. The so-called Bedrette lab, a laboratory of ETH Zurich, was established. And this object is really unique due to its geological conditions. This is why some geomechanical research with LiDAR scanning has already taken place there, but only on certain location. Our goal, however, was to scan the whole length of the last 3 kilometers from 2000 till tunnel meter 5000. For this purpose, the represented device was used, a laser scanner of Teledyne Optec. And depending on the geometry, on the complexity, the distance between the two scanning points was chosen between 10 and 15 meters. So it took us longer than 1 week to do it all. The next stage would be data processing, and next step here would be merging the separated point clouds into one object, which was sometimes challenging due to high resolution. So we chose the maximum length of segments of 200 meters. And it was also challenging because the tunnel has really few notable features. However, that was achieved, sometimes manually and with the ICP algorithm, and we decided to cut the cross sections for further representations with the density of 10 meters per each. The next step would be, however, the most important and the most challenging. This would be co-aligning the so-called ideal geometry with the real geometry of the existing tunnel. And it is really difficult to find some objective reference. And when I was in the tunnel inside, I decided to use the rails for that. That was not an ideal decision, but probably the only possible one here and the most suitable one. The next step would be calculating the distances with a very straightforward, easy function, such a cloud-to-cloud distance, and unwrapping the whole thing for the simpler, for the 2D representation. And this what the final result look like. Below you can see some cross sections which are representing some kind of supporting plots for the better understanding of this 3D plots which are not as easy to read if the person has not spent enough time with that. But however, we can see the left side of the tunnel, the left wall on the left side of each plot, the right side, the right wall on the right side of each plot, and the roof somewhere in between. And these 5 plots, for example, represent a whole segment of 125 meters. And we'll see that in most cases, there were more deformations or bigger distances on the right side. The same was done for each of the cut cross-section, but manually. So we measured some properties. So these are just 2 graphs, 2 geometrical characteristics, and each point represents 1 cross-section, and the cross-sections, their geometrical properties are plotted against the tunnel meter. Probably, we can say, against the coordinate. And we really see some important geological correlations here, like that we have bigger cross-sections, let's say larger deformations in the places where the rock mass is more structured, where the material is loose, and so on. So to sum up, we could only manage to investigate around 80% of the whole tunnel's length, because even in such a perfect object like Bedreta Tunnel, we don't always have direct access to the raw rock mass. Also, it was, as mentioned, we saw some strong correlations between geology and the geometry, and probably the most important conclusion is that being at the site, investigations influences the workflow of the data processing and vice versa, because sometimes we need to face the decision which we cannot face without being at the place, without knowing the history of the project and so on. So the collected data set has already been used and being used in the further geomechanical research in Switzerland and Germany. The provided technique for the plotting has been used in some journal and conference papers for geomechanics, and we're also going to probably publish one more paper which will describe the whole workflow more comprehensively. And of course, similar approaches can be used for the characterization of other similar linear objects, but it's always important to adjust them, knowing the history and the context of each object. And of course, thank you for the attention, and I'm welcome to answer some further questions, whether online or here at INTERGEO within the next 3 days at the stand of my company, Geoconsult. Thank you so much.